Chapter 4, Energy from Combustion, Part 4. We're going to continue on with the chemistry of gasoline, look at catalysts. You may have heard of your catalytic converter. That's a type of catalyst, biofuels, and the way forward. Let's check out a video on the topic of thermal cracking. There's an optional historical video as well, which is neat. Thermal cracking is essentially when a mixture of alkanes from crude oil is heated at high temperature, and when this happens, the molecules break apart and rearrange. They rearrange to something called a branched alkane, and we'll be looking at that in a little bit. And those branched alkanes tend to work better in your engine. They decrease knocking. We'll also explore that a little more in a moment. Catalytic cracking is similar to thermal cracking, except a catalyst, often a metal, is added to speed up the process or make it more efficient. Let's first, before we start talking about branched alkanes, bring up the topic of an isomer. So here we have a molecule with 8 carbon atoms, so that's 8 like an octopus, or octane. And this is also a carbon-based molecule with 8 carbon atoms, but it's named a little bit differently. We're not going to go into the naming of this molecule, but it is an isomer of octane, meaning it has the same number of carbon atoms and hydrogen atoms as octane, but the bonds are in different positions. Instead of all the carbon atoms laid out one after another, we've got them jutting off this main trunk of the molecule like branches. That's why these are called branched alkanes. So again, isomers, same number of carbon atoms, different connectivity. Where the bonds are located are different. In order to figure out if a molecule is an isomer of another, first you have to make sure it has the same number of atoms. Let's explore this a little more by watching a video. Thinker Buddy question. Which is the same structural isomer as the isomer of hexane shown? We've left out the hydrogen atoms. So here's an isomer of hexane. It's got 6 carbon atoms, but instead of them all 6 in a row, like N-hexane, we've got 1 off the middle carbon. So which one of these is also an isomer of hexane? The correct answer is A. If you went through and counted all the carbon atoms, you would see they all have the same number of carbon atoms. But only A has that carbon atom coming off that middle carbon. 1, 2, 3, 1, 2, 3. That's where the carbon atom lies. This would be a different, but also a structural isomer of hexane. B would be acceptable. D would be considered hexane itself. It doesn't matter where you put those carbon atoms, because when you have a single bond, they actually freely rotate willy-nilly. So the whole molecule is kind of very active, twisting and turning. So where you draw them on paper doesn't matter as far as where they are relative to one another. What matters is what carbon atom you attach them to through a bond, however. Let's look at a short video on how combustion occurs. So here we're showing a simple combustion engine, and essentially the fuel comes in, a spark plug ignites the fuel, it combusts. The energy released does work and pushes down the cylinder. This happens many, many times a second maybe. Okay, so now you've seen combustion in action. Knocking occurs when the timing of the ignition is off. So we have the spark plug with the ignition, but the combustion doesn't happen when we want it to. Premature combustion, and that causes this shuddering or shaking or knocking sensation. And if you increase the octane rating, and this is particularly true with sportier cars, you often have to use a higher octane gas because they're very finely tuned to improve their performance. So something called 2,2,4-trimethylpentane, and the way they named it is basically 1, 2, 3, 4, 5 carbons on this main trunk, and then there are 1, 2, 3. These are known as methyl groups. We drop the ANE and add a YL when we have a 1 carbon branch. And then we just put the number for which carbon they're coming off of. So we would number this particular one 1, 2, 3, 4, 5. You do not need to know this. You do not need to be tested. You will not be tested on it. I just wanted to, just more of an FYI. This is also known as iso-octane, a nice simple name. But we've standardized our octane rating testing, giving this molecule 100. It knocks very little. Heptane knocks a very large degree. It's quite a knocker. But you can see here that methanol has even less knocking than isooctane. Ethanol and MTBE, we'll look at MTBE in a moment. And octane itself, strangely enough, has a very poor octane rating. It knocks quite a bit. And that's because it's unbranched. Your car, in order to control the combustion, likes branched alkanes, not these straight alkanes, these straight hydrocarbons. That's why we do thermal cracking. So here we just have a picture of what you see at your gas station whenever you fill up your car, or if you're awesome and take public transportation or bike, you don't have to worry about this. But of course, this 93 is basically saying whatever they formulated for that particular company for that super unleaded gasoline, when they test it, it has an octane rating of 93. It's very comparable to our standard of iso-octane, which knocks very, very little. Maybe it's not quite as good as pure ethanol, which has an even higher octane rating. But ethanol is actually more expensive to produce than gasoline. Gasoline we take out of the ground and just refine it a bit. Ethanol, we actually have to do more work. Let's talk now about some gasoline additives. Tetraethyl lead was used quite a bit historically to increase octane ratings. You just have to add a little bit. But this would be leaded gasoline, and it was a problem. It led to more pollution. There's the poisoning, the toxic quality of lead itself. Even small amounts can cause developmental disorders in children. So we've gotten rid of that and instead replaced it with MTBE. Again, don't worry about the systematic name. But this has a very high octane rating, and I'll show you the structure in a moment. It basically contains an oxygen atom, which improves its ability to combust. The only problem is it's very, very persistent in the environment, meaning it sticks around. It doesn't break down. And we don't like chemicals that don't break down, because if they have any toxic qualities to them, we're in trouble. that was part of the problem with CFCs in the ozone layer, right? They did break down to some degree, but that chlorine radical stuck around for quite a long time, continuing to destroy ozone. And what we've actually found is MTBE in our water reserves, groundwater reserves, and there are actually millions of lawsuits due to contaminated drinking water with MTBE. Some people have started phasing it out. The EPA is looking at it more closely. It's a bit of a mess. Then we have ethanol as a gasoline additive. Most gasolines you put into your car already have ethanol. It improves the octane rating as well, but it's not abundant. It's not as abundant, and it costs quite a bit to produce. So when you have these additives with something like MTBE or ethanol, we have these oxygen atoms. Those oxygen atoms are improving the combustion, reducing knocking. These are our oxygenated gasolines that contain molecules or additives with an oxygen atom in their structure. Reformulated gasolines are oxygenated gasoline that reduce their content of hydrocarbons that evaporate readily. So they must be, these gasolines, reformulated gasolines, must be at least 2% oxygen by mass. So they have to add a lot of additives in order to reach that target. So a fair amount of ethanol usually is what they add. Maybe some MTBE, but I would much prefer they use ethanol. Of course, it's more expensive, and we all don't want to be hit too hard at the gas pump, although that would probably encourage development of better public transportation in the US at least. These reformulated gasoline requirements came about due to the Clean Air Act in 1990. Many large industrial or urban cities have instituted laws mandating that only reformulated gasolines are used within city limits in order to reduce pollution, right? We don't want those VOCs, those volatile hydrocarbons, emitted into the atmosphere, contributing to the production of tropospheric ozone and smog, and trying to reduce that as much as possible is going to reduce the pollution of these large cities. Thinker buddy question. There are many relevant aspects to the use of gasoline as a commodity. Which statement is correct? A. Gasoline is a mixture of molecules that includes many hydrocarbons. B. Octane rating is a misnomer because the molecule octane has a terrible octane rating. C. Oxygenated additives like ethanol help lower auto emissions and raise the octane rating. D. All of these statements are true. Gasoline isn't made of octane. It's many different hydrocarbons. And octane itself, if it's a straight chain molecule, N-octane has a very poor octane rating. It's the branched isooctane that was set to our standard of 100. Thinker buddy, what is meant by the term reformulated gasolines, and why were they developed? Reformulated gasolines contain A. Dissolved oxygen gas, and therefore burn more cleanly than regular gasoline. B. Both octane and isooctane were developed to improve octane ratings. C. Oxygen-containing compounds, and were developed to meet mandates of the Clean Air Act and its amendments. D. MTBE as an additive, and were developed to meet water quality mandates in California. The correct answer is C. It's not oxygen gas. It's oxygen-containing compounds, compounds with an oxygen atom in their molecular formula. And it was a concept developed along with the Clean Air Act. So definitely not A. It's not oxygen gas. Octane, very poor octane rating, so that's not correct. And MTBE was not developed to meet water quality mandates. It's actually a big problem in terms of water quality. So let's talk about catalysts. This is a picture of your catalytic converter if you have one. You can see NOx, carbon monoxide, unreacted hydrocarbons, all coming into your catalytic converter. And what happens is there's a ceramic substrate, usually with platinum on it. And that catalyst lowers the energy of activation, makes it easier for these molecules to finish their reactions, combust properly, so we get carbon dioxide and water and nitrogen gas, things that are not great. We don't want a lot of carbon dioxide, but at least we're not getting NOx and VOCs out the tailpipe if we have a functioning catalytic converter. There will still be some that escape, but the catalytic converter helps. And more specifically, it essentially holds those volatile organics and other compounds to this substrate and makes it easier for those to break apart and react with oxygen. So a catalyst lowers the activation energy. This is a more accurate energy diagram than the ones we've seen in past chapters. It's not just a one step down. We have this initial energy that we have to put in to do what? We have to break bonds. The first thing we do in a reaction, we break the bonds between the atoms. That always takes energy. You always have to add energy to a reaction before you do anything else. Yes, when the new molecules are formed, you release a lot of energy if it's exothermic. Great, but you always have a little activation energy. What a catalyst does is lower the amount of energy necessary to break apart the atoms. Which line segment in the diagram represents the activation energy for this reaction? A plus B goes to C plus D, a generic reaction. And on the right here, we can see the reactants A plus B about part way up the graph, and then a little hump, and then the products down towards the bottom of the graph, C plus D. So is it number 1, the arrow going from the products to the beginning of the reaction, just straight up measuring that energy difference? Or is it from the same horizontal line as the reactants to the top of the initial peak? Or is it from the same horizontal line as the reactants to the products? And then the final one is just from the very top of the initial upwards peak all the way down to the bottom. So the activation energy is number 2, where you go from the horizontal line, you draw out the horizontal line from the reactants and draw an arrow up to that initial little peak. That's the energy we have to input to break bonds. Which graph shows an endothermic reaction with curve A being the catalyzed reaction and curve B being the uncatalyzed reaction? If you can't see the graphs, try to draw out an endothermic reaction with 2 different curves, one being the catalyzed and one being the uncatalyzed, or perhaps describe it. The correct answer is D. The endothermic reaction must have the products at higher energy than the reactants. You always have, going from reactants to products, this initial activation energy and then some energy release, but how much energy release depends on the reaction you look at. It's different for every reaction. And then A, this is showing our catalyzed reaction. Why? Because that activation energy is lower. Please watch the following video on biofuels. I would also recommend reading your text before working on the homework to expand upon any ideas mentioned in the videos. So where do we go from here as far as energy demands and consumption? Well, here we can see the energy uses so far, and mature market economies, say industrial nations, we're planning on using more and more energy. Emerging economies going to see a sharp increase in their energy demands. So what do we do? Another thing to keep in mind, you just can't necessarily cut your energy use. If you look at the relationship between energy consumption, don't worry about this unit, but just notice a trend. Energy consumption and the Human Development Index, which gives you some information about the quality of life, you could see that the more energy used, typically the higher quality of life. So we can't just stop necessarily using energy. We can use energy more efficiently, more effectively. We can find alternate ways to produce that energy, and we'll talk more about that later in the course as well. But you can't essentially say we're going to stop using energy. This ends Chapter 4, Part 4, and is the final lecture for Chapter 4.